In a previous video, I described what the laws of proportionality are. I showed you the voltage law of proportionality, and I showed you the current divider. And we talked about how we sort of manipulated this formula and added 100%. So I'm not really going to cover how we came up with this formula, but I'm going to show you how you can use this to solve combination circuits without really breaking them down. And I think once you understand how to do this, you'll fully understand how current moves in a circuit, and knowing that, you can solve for any circuit. So first thing we got to do is we got to find total resistance. And as we do this, we are going to be writing down the equivalent resistance of each branch. And that is going to allow us to use this formula to solve this without traditionally breaking it down into one resistor and then building it back up. So you guys have all done lesson 4. So I know you guys know how to do combination circuits. So let's just see how can we use this without really breaking this thing down. So let's just start on this side here. We have R7 equals 60 ohms, R8 equals 20 ohms, and R9, which equals 80 ohms. We can see all three of these resistors are in series, and we know series resistance just adds up. So if I take 80 ohms plus 20 ohms plus 60 ohms, this will give me the total for R7, 8, 9. 80 plus 20 is 100, plus 60 is 160. So the equivalent resistance of R789 is 160 ohms. Now we can see that R6 is in parallel with R789. So I need to combine these two resistors in parallel, and that will give us the equivalent resistance of this little branch here. So we can just use the reciprocal method, and then that will give us R6 inverse plus the inverse of R789, which is 160. And then we inverse that whole thing. And when we do that, we find out that our 6789 has an equivalent resistance of 32 ohms. So I'm just going to write that up here. The equivalent resistance of our 6789 is going to equal 32 ohms. And now we can see that R5 is in series with R789. So series, we just add those two together, and we are going to have the equivalent resistance of this branch right here, which would be R56789. And that will equal 60 ohms. All right, let's do the other side. Let's do the other side. We can see that we have R2, 80 ohms, R3, 40 ohms. Those are in series with each other. So if we just pretend that these are one resistor, this would be called R23. And that would equal 80 plus 40, which is 120. And now we can see that we have R23 in parallel with R4. Combine those using the reciprocal method. 24 inverse plus 120 inverse. Inverse the whole thing. This will give us 20 ohms. So the equivalent resistance of this branch over here will be R2, 3, 4, and this will equal 20 ohms. I'll write that down here, 20 ohms. Okay, so now we have two branches in parallel. We have a 20 and a 60. So we need to combine those two in parallel. Just do the reciprocal method again. 20 inverse plus the 60 ohm branch inverse, and that is going to equal 15 ohms. And then what we have is we have those two branches, and they're both in series with R1, and we have 15 ohms in series with a 5 ohm resistor. This means our RT for this circuit is going to be 15 plus 5, 20 ohms. And we got our total voltage, so that means we can get our current. So let's go down to our pure chart here. We found that our total resistance is 20 ohms. And if we take 800 and divide it by 20, that will give us our total current for this circuit, and then we can start moving forward. It's going to give us 40 amps of current. So let's see what we can do with this 40 amps of current. We get rid of some of these red marks here. RT. We'll just do current in orange. So we know our IT is, 40 amps. So let's follow the current's path. We know if I have 40 amps leaving this battery, I know I have 40 amps coming back, right? Nothing consumes current. Whatever leaves the source returns to the source. That means my current for I1 needs to be 40 amps. So I can write that down here. Current for R1 is 40 amps. Come back up here. We know it's going to split. This is where this formula comes in. If I have 40 amps coming into that junction, I can manipulate this formula to figure out whatever branch I want. Let's figure out this branch here. So that means I am going to have 40 amps, and I'm going to multiply that by 100% minus the branch I'm looking for, which has an equivalent resistance of 20 ohms, over one branch plus the other branch, 20 plus 60, which will be 80. Parentheses, parentheses. If I do this, this should tell me the current that is going to go to the left. So 40 times, parentheses, 100% minus 20 divided by 80, 30 amps. I am going to have 30 amps head this way. If I have 30 amps going that way, Kirchhoff tells me that I must have 10 amps go this way. Let's just solve for the left side of the circuit. I'm going to erase this formula here. This junction right here, I can manipulate this formula again. I have 30 amps going into this junction, and that is going to multiply by 100% minus whatever branch I'm looking for. So let's see. Let's look for R4's current. So we'll put the resistance of R4 on top, 24 over R4 plus the equivalent resistance of R23, which is 120, 144. Let's see what that is. 30 times 100% minus 24 over 144. That says I am going to have 25 amps going this way. And if I have 25 amps going that way, that means I have 5 amps going down. 30 amps coming in, 25 amps coming out, 5 amps going down. So that tells me my current for R2, 3, and 4. R2 and 3 are in series. They're both going to have 5 amps. So let me write those down here. R2 and 3 both have 5 amps. and R4 will have 25 amps. So that solves for the whole left side. Let's sort of draw this out though with what we got. You got 30 amps coming in, 5 amps coming down, 25 amps going this way, and now you have 25 amps and 5 amps coming into this junction, which means all the current adds together, and this is going to be 30 amps heading towards this junction here. Let's solve for the other half. That means all that current has to go through R5. That means the current for I5 is 10 amps. I5 would be 10 amps. We have 10 amps coming into this junction right here. One branch is 40 and the other branch has an equivalent resistance of 160 ohms. So let's plug that into our formula that we have down there. We have 10 amps coming into a junction that is going to multiply by 100% minus the branch we're looking for. Let's just find the current through R6. So that R6 is 40 ohms, and that's going to be over the equivalent resistance of R6, which would be 40, plus the equivalent resistance of our 789, which is 160. That would be 40 over 200. So plug this into the calculator. 10 amps times 100% minus 40 ohms divided by 40 plus 160, which is 200. 8 amps. If I have 10 amps coming into this junction and I have 8 amps coming down, that means I gotta have 2 amps go out that way, and that solves for this whole circuit. I now have the current through R6, and I now know the currents through 789. We'll plug it into our formula. R6 is 8. Our 789, all in series, all going to see that 2 amps of current. Now you have 2 numbers for each value. You can now use those 2 to solve for the other 2 missing values, and this circuit is done. Let's just look and see how this current flows through here real quick, and then I'm going to stop it. So right here at this junction, we have 8 amps coming down, 2 amps going this way. That current's going to go through R7, R8, and R9. I have 2 amps and 8 amps meeting up in that junction, and that is going to have 10 amps come out. 10 amps is going to meet up with my 30 amps, and that will give me 40 amps going back to the source. I hope this works for you.